Well, welcome back, class. We're going to be talking about refrigeration as it applies to the air conditioning. This particular PowerPoint was produced by Mr. Baldoff and adapted by myself, Denny Purdy. So I hope you learn a lot about the refrigeration as it applies to the air conditioning side of the industry. So, air conditioning is comfort cooling. It is really high temp refrigeration applied to a space temperature of a building to cool it during the summer months. The sun path is directly over the occupant's house during the summertime, and the sun's path during the wintertime is more at an angle towards the front of the house. Now, as the sun is moving in the summertime over the top of that house, we're going to get a couple of different ways that heat is going to enter into this structure. And remember, the whole purpose of air conditioning is to move that heat out of that structure so our occupants in that structure can be more comfortable as they are going through those summer months. Now, three ways that heat's going to enter in to the house is conduction is one of those ways. Conduction can be done through the walls. Conduction can be done through the ceiling itself as that attic is heating up. Uh, so any place that the warmer area or the hotter area is in contact with a cooler area, we're going to get that transfer of heat and the conduction through that structure itself, but mostly through the walls. Another way that heat's going to enter the structure is through radiation. As the sun is pounding on that house on the east and on the west through the windows, it's going to be heating objects within that house and also the windows themselves, and that heat's going to travel into the house, and that's the type of heat that we want to try to remove from the house so the occupants can be comfortable. Now, a couple of ways that we can mitigate that type of heat coming into the house is putting low E windows in, or possibly dropping our shades down fully so that the sun is not penetrating through to the structure itself and heating the objects within that structure. A third way that heat's going to be entering into the structure is done through cracks in the foundations, uh, bad weather stripping on doors and windows. If we end up structurally, like let's say our foundation is starting to sag a little bit, we end up with cracks in our ceiling. Well, that air is going to be moved out, and we're going to be replacing that air with outside air coming in. Anytime that you're dealing with ventilation, as in exhaust for bathrooms or exhaust for kitchens, natural convection or natural drafts for water heaters and stuff like that, we're going to end up moving conditioned air out of the environment, and then we're going to be replacing that air, and that's the infiltration that's coming in. Now we're bringing in hot, moist air into that structure, so we're going to have to condition that, and if we can avoid bringing that air from the outside into the inside without conditioning it first, then we're going to have a better opportunity to provide that comfort that the occupants are looking for. The sun's path in the summer moves from east of the house in the morning, sits over the top of it, and then just pounds on that roof, and it enables it to get hotter and hotter. And like I said, in the wintertime, the sun has a more uh, frontal path on the house itself, and that has to do with the azimuth angle of the sun and the altitude angle of the sun difference from the summertime to the wintertime. So, one of the ways that we can prevent that conduction heat from entering into the structure is to try to keep that attic as cool as we can. Now, there's a couple of different ways that we can do that. Power wise, we can use attic ventilation fans, and that can be AC coupled fans or solar DC fans, are a couple of ways. And then we can also use something called a natural ridge vent, or vents that are providing natural convection of that heat out of the attic space. Remember, as we can keep that attic as cool as possible, we will prevent that heat from actually being transferred into the environment down below. So attic ventilation fans are a great way to do it. The diagram on the left shows us an attic ventilation fan right here. But don't just go off and buy an attic ventilation fan and install it. You have to be sure that the place where these fans are located is going to be the most effective in moving the heat from the environment. A lot of houses have on the bottom down here what we call ridge vents. A lot of roofers are installing ridge vents into that structure. So if we were to introduce a attic fan into a ridge vent situation, and that attic fan would happen to be really close to the ridge vent, well, we would only be taking out. Let me get this off here. We would only be taking out the heat that was in the upper portion up in here, because the ridge vent that sat at the top of the ridge would actually uh, it would take the path of least resistance, and the air would be sucked in there and then jettisoned out of the attic fan itself. So I don't want to see that happen. I would rather see the attic fan being put in, and then our actual down in the corners, our soffits. If we had a nice little overhang over here, and we had our soffits sitting there, that air would be pulled up our soffits into the attic fan, and that would be a better condition for us to remove the heat in that structure. Not saying that you can't install an attic fan with ridge vent. It's just that practical, reasons, and when we're dealing with a path of least resistance of airflow, it tends that the attic fan will suck through that ridge vent. Now, we can also do it naturally. Put this ridge vent in, and then you have soffit vents that are sitting at the bottom of our roof, and that's going to allow that air to be drawn up into the soffit, and take that heat out of the structure. Now, when we're dealing with specific attic fans, we have to understand that the typical temperature at which they're going to be turning on is somewhere around 85 degrees for that structure. Attic fans and solar DC powered fans have overloads on them that prevent them from operating. If there was a fire that was started in the attic, we don't want to feed that fire with new oxygen. So those attic fans will have safeties that will prevent those fans from operating at that time. So infiltration is a really probably the main source of heat gain for a house. The windows, the doors, crawl space, cracks in ceilings. If you ever done a blower test on a door, you would find infiltration in multiple areas within that structure. And it's always best for us to prevent the conditioned air that we have from escaping that space, and that's going to be able to save us the most amount of money um, for that structure and for that individual who's running it. So if we're having problems, controlling humidity within the house, it's probably due to infiltration. So check your windows, make sure that they have good window seals around them. Check your doors. Are they rated for outdoor use? I mean, mostly new construction, they're going to be doing this correctly. But if you get into older houses, sometimes they want the cheap route, and they put hollow core doors on instead of a solid or core filled or foam insulated doors themselves. So, really, as an HVAC technician, you are going to be getting into the total comfort or the total construction of this house and how it's put together to help you to maintain comfort for that individual. Crawl spaces are a source of humidity coming into the house. So, is there a vapor barrier down in the crawl space? Are there paths for air to move into the house from the crawl space? And that's going to be a problem not only in the summertime, but also in the wintertime, as we are, moving that heat out of the house by natural convection for cracks in the windows and stuff with crawl space openings that are open to the house themselves. Cracks in ceilings are another place for air to move out of the house or air to move into the house, depending on the type of negative pressure or positive pressure that's given to you from that. So these are just some things to look at as an HVAC technician when you're working on different aspects of comfort for that house. Now, how can you fix this stuff? Well, we're not window technicians, so we were just trying to identify where these infiltration places are, and doing our best to inform customers about how they can fix those particular items on it. Now, that might be hiring a professional to come in and seal the house. Uh, Sealing the house is a very effective way of preventing infiltration. During the construction of the house, plumbers, HVAC technicians, electricians will drill holes into the studs and then up into the plates in the ceilings. And you don't see them because they are behind the drywall and behind the plaster walls. But if they didn't seal those holes, you're going to get air movement from the actual structure out through the attic space. So sealing up holes is a very effective way of preventing infiltration coming into that house. Well, like I said before, humidity is a huge concern for us in the wintertime and also in the summertime. I had an instance of a crawl space that was open, that they were sucking air out of the crawl space and then blowing it into the house themselves. We had a dew problem, moisture problem on the windows. They thought it was a window problem. Window guy came out, replaced the windows, and it happened to be a moisture problem from the moisture in the crawl space. So the way to prevent that from happening, we suggested that we put a vapor barrier down in the crawl space, but also that we tie the ductwork into the actual piece of equipment so we're not sucking crawl space air into that. And I know that sounds like poor construction, but that's the way that we used to do things. And if there's no codes to say how the equipment's going to be installed, well, then you can have anybody come out and install this equipment and not understand how crawl space air may not be the best type of air to be uh, breathed in for our consumers themselves. So be really concerned about the comfort of our different individuals out there, health concerns as well because of mold and mildew that could be in that moist type of air. But infiltration is a huge issue when it comes to load calculating and comfort for our customers. So as far as we're dealing with comfort cooling, there is another way that we can accomplish cooling within environments that have really dry climates. That device is called an evaporative cooler. It has been used for years. Evaporative coolers are also commonly referred to as swamp coolers. Water slowly runs down the fibers mounted in within the evaporative cooler itself and the frames on the inside of it. And as fresh air is passed over that evaporative cooler, it's going to evaporate the water to the point close to the wet bulb temperature of the air. Now, the air entering the facility is very moist, but the air temperature is well below that of the dry bulb temperature. Now, we're going to be using this in a lot of different environments that are very dry, such as in deserts. You might see these in Arizona, for say. One of the characteristics of an evaporative cooler is that it is 100% outdoor air coming into the facility. Because we are pushing 100% outdoor air into the facility, we're going to need a discharge point somewhere in the house where that air can leave the house. And like I said before, that the evaporative coolers are going to be used in low humidity locations, so that we can provide cooling to individuals without mechanical types of refrigeration. Looking at the different types of evaporative coolers, we have a drip type. which is shown in the book and also on the PowerPoint that you guys are viewing right here. Sling and sprayer type, and then rotary type. The drip type, we are just dripping water over top of a media, and then air is passing over that media. The spray or slinger type, we are spraying that moisture up into the airstream itself. It is again going over a piece of media that the air is passing through. And then rotary type, we have a rotary motion or a rotary fabric that's rotating into the water, and then as it comes out, the air is going to pass over it, and then we're going to get evaporation off of that, cooling that air down to the wet bulb temperature of that air. And those are your three different types of evaporative coolers that you'll see within the field. As we continue to talk about the refrigeration process, remember, refrigeration is taking heat from a place where I do not want it to a place where it makes little or no difference that I've placed that heat. And the four major components of the refrigeration process are compressor, condenser, expansion device, and the evaporator. And remember, for reference sake, that these different components are doing exactly what they say they're doing to the refrigerant that's in the actual system itself. So the compressor is taking it, it's actually creating that low pressure, low temperature situation on that side of the system, the sucking, the low pressure side of the system, and it's compressing that refrigerant so that we can build the head pressure on it, and that we can raise the pressure and the temperature of that refrigerant to so that when we send it into the condenser, we can remove that heat from that refrigerant that's in there to the outdoor air. The expansion device is a dividing point of the low side and high side, just like the compressor is. But in this component, we're going to meter that refrigerant through a small hole, expand it out into a large area, and then we're going to see a pressure drop on that refrigerant as it does that. Remember that the heat has already been taken out of the refrigerant by the condenser, because it's going to condense that refrigerant from a vapor into a liquid by removing the heat of it. And then also we are going to subcool that refrigerant down so that we are able to increase our capacities on our systems themselves. The evaporator is going to take that liquid refrigerant, going to pass air over the evaporator, and that heat's going to be absorbed by the evaporator into the refrigerant. And that refrigerant that's in liquid state is going to turn into a vapor state by boiling that refrigerant off. Now we have certain pressure temperature relationships that go on with our systems, that we are able to calculate superheat and subcooling on our systems to see how well the system is working, how full the evaporator is, and how much heat we picked up and how much heat that we have rejected in the condenser itself. But that is your basic refrigeration process. Continuing on to the different types of packages, types of configurations of units that are out there. We have package equipment, where all of the components are built into the cabinet, much like a window air conditioning unit. We also refer to these as self-contained equipment. Rooftop units would be another description of them. Ground-mounted rooftop units are also another description of these types of equipment. Air is ducted in from the equipment into the facility, either through the roof curb or through ductwork that we are attaching to the unit itself. Package equipment may be located beside the structure, on top of the structure, but in some instances, the heating equipment is built into the cabinets as well. We can have electric heat, we can have gas heat, propane heat as well for these different types of units. Referring to the package units, something that's very nice about outdoor equipment is our ability to use what we call free cooling. So if the humidity level is correct outside and if the temperature is correct, we can take that air that is on the outside and then push that air into that environment, cooling that environment down. It is known as an economizer package. A lot of rooftop units come with economizers, and with the economizer, we are actually cutting the cost of running commercial. Running the refrigeration process and using free cooling from the outdoor. So we're going to use the blower. We're going to suck in the air from the outside, and then we're going to dump that air into that environment. Uh, we have to be weary of the amounts of humidity that's in the outdoor air because we don't want to dump a bunch of humidity into that environment. Otherwise, we're going to defeat the purpose of what's going on. Now, uh, with our economizer, we usually have two stages of cooling. One stage will be the compressor, and then the other stage will be the economizer. The first stage is the economizer when the air temperature is well below what our conditions are and abilities to cool that place down. So the first stage will be the economizer. We'll open up that damper, allow outdoor air to come into it, and then if we are still requiring additional cooling in that area because of the heat load, we can kick the compressor on and provide mechanical refrigeration for our unit to start to work. Well, we're continuing to look at the types of air conditioning systems that we have within our field. The first thing we're going to be looking at is a split air conditioner, where we're going to have a furnace or an air handler in the vicinity of the place that we're wishing to cool or heat. And then we are going to have an evaporator coil sitting on top of a furnace or inside of an air handler that's going to provide the transfer of heat that is required to cool that facility down. We refer to these units as split air conditioning systems. The condenser is located outside, remote from the evaporator, which means that we need interconnecting tubings known as refrigeration lines that are supposed to be field installed by a service technician that runs from the condensing unit, maybe through the crawl space, maybe through the attic, into the indoor unit, where we will braze those two pieces of equipment together with those interconnecting tubes so that we can provide cooling for individual houses. The blower that moves the air moves it across the evaporator, either sitting on top of the furnace or in the air handler itself. So the air handler may be used instead of a furnace, where the coil is going to be sitting inside the air handler, and the coil for the furnace will be sitting on top of the furnace. In the picture that we're looking at to our left, what we have there is we have a condensing unit that's sitting outside. We have our interconnecting tubing for our refrigerant going to a coil that's sitting on top of the furnace. And then here is our evaporator coil on the inside. Now, this may be ran in a crawl space. This may be ran in an attic for our ductwork, or the system may be put in a closet and then used in an upflow manner or a downflow manner for the refrigeration, for the air that's moving through that system itself. Electrical disconnects, as seen right here, is our electrical disconnect. It's sitting on the outside of the building, and it's located there. We will run our lines from that disconnect switch and down into our condensing unit, making sure that we're running that piece of electrical liquid tight connection with the line sets to make it look nice and neat for our customer. I do not like the way the picture is depicting us running straight across with our lines right there. So if you can avoid doing that, do that. We will have individuals who will walk between our units. I know that electrical prevents them from doing that. It doesn't look as clean as an installation as it could in that area. Also, the condenser is going to be sitting on a concrete pad or a rubber pad, and we're going to make sure that the condensing unit, when it's sitting in this location, is going to be nice and straight, level for our unit. Going into the service aspect of this field, whenever we approach any unit that is out of level, we want to make sure that we're carrying some sort of stone with us in a 5-gallon bucket so that we can lift that condenser up and actually level that condenser for it. This is going to help the oil within the compressor to stay level, plus the appearance of it uh, being unlevel from one position to another really makes it look bad for the homeowner, bad for the technician who decided to leave it that way. So we want to make sure that we are hooking these units up and maintaining them in a way that the appearance of them is professional in that application. Looking at the ductless split system, they come in various styles and operations, heat pump applications, as well as air conditioning. We have a cassette that's sitting on the wall, and that's the picture that we chose for this mini split. But there are a wide variety of ways that we can hide those cassettes now. We have the ones that sit inside the wall. We have the ones that recess into the ceiling. We can put them into a grid type design and use them in that way. We have floor mounted models. We have models that are low static where we can hide the actual unit and then duct it into multiple rooms and not just one room that we're looking at trying to heat or cool. These systems are used in many residential applications, such as additions, renovations, home preservation projects, garages, attic conversions. Sunrooms would be another way that we can use this application. We just decided to finish the basement downstairs, and that provides a little bit of a challenge for us in heating and cooling that. Well, we don't have to use the main heating source of the actual house and put in zones for it. We can actually drop a mini split down there and maintain that area very, very well for it. Not only can you use mini splits in a residential application, but we can also use it in a commercial application. Let's say that we have a dining room in a restaurant, computer room, churches, bars, um, just to name a few of the other areas that we can place those mini splits. So the biggest advantage of a ductless split system over a conventional system is the ductwork free design that this system has. Conventional split systems with ductwork, they have the potential, according to the Department of Energy, to lose as much as 30% of their airflow due to air leaks within the system. So there you go, 30% of the conditioned air that you had in it is going to be moved out of that particular area. So we'll finish up this ductwork. The last thing we were talking about is the loss of the BTUs or the airflow through that ductwork, which doesn't happen with our mini split types of systems that are out there. The one drawback that we do have with mini splits, and they have been working on this, is the appearances of them sitting on the wall. It's they're ugly, to put it plainly. Especially the cassettes that are pictured here on the outdoor. They're very slim, and they're difficult to work on, but very slim for the appearance for the outdoor. But the indoor units make them less desirable to put in. Many manufacturers of ductless systems have tried to improve that fan coil unit appearance by making them look less obstructive in the living space. And we talked about a couple of different ways that the manufacturers are doing that. Well, one manufacturer has even created a fan coil unit that looks like wall art. So it will pop out of the actual wall, cool the facility, and then close back up. These systems require precise heat gain, heat loss um, if they were the only equipment that's going to be cooling or heating that particular facility on it. So we would need to do a heat loss of that particular room or that particular addition that was going in there, and then install our mini split application in that area. Now, when we're dealing with mechanical refrigeration, There's a couple of different aspects of it that go into it. We are really referring to the cooling, the dehumidification of the air when we're dealing with air conditioning, air movement that is not taking, not being uncomfortable for the occupant that's in that room. And honestly, when an air conditioner is running, we should not be able to hear that air conditioner run if the ductwork was sized correctly and the unit was sized correctly for the house itself. So air movement's very important. Air filtration is important too. With a lot of individuals having allergies, we want to make sure that we're filtering the air very well. Um, Not so much done well on mini splits, but a whole house air conditioner. We can put some really good filters on those units with the ability to catch many particles of viruses, bacteria, pollen, and dust to help the individuals breathe within that house. On the aspect of humidification, when we're talking about those areas that are dry but yet need that type of cooling, such as the desert areas, we'll be humidifying that air as well as cooling that air. So what we have here is the indoor section of our air conditioner. This happens to be a York furnace with a horizontal H block type of evaporator coil that we're looking at. So your indoor section of your air conditioning encompasses the evaporator coil, the metering device, the air handling device, and the filter for that particular unit. This one happens to be beneath this York furnace, clear at the bottom of it, and I'll highlight it so that you guys can see it. Right down in here is where they're going to be putting the filter in. We look at this, and it is a gas furnace. The gas furnace is coming up into a H block type of evaporator coil at the top of the furnace itself. And this is going to be typical of any type of unit that you have out there. We see the drain line that's going to be ran for that unit. We have a trap sitting right there on that unit as well. And what that trap is going to be used for is to keep bugs and other items out of the evaporator from crawling up into the drain and getting in to our airstream and ultimately into our house from that environment. The drain can be ran to a natural drain on the floor drain, or we can run it into a pump and pump it up to a different location if we wanted to do it that way. But otherwise, the water comes from us cooling the air down, and then the air actually condensing, the moisture actually condensing on the evaporator, and then draining out of the drain itself. Now, there are certain um, pitches that we have to have the drain line at, and a good rule of thumb for that is every foot you should be dropping a quarter of an inch for your drain lines to drain out properly. You do not want to drain your drain lines out too fast, otherwise sediment would end up in those lines and stuck in those lines as well. We can glue these traps together, but there is a trap out there that's in a clear coated uh, plastic that enables us to look inside of it and see whether we need to clean it or not. During the normal service of an air conditioner, this is one of the things that you should do to clean out the trap on the evaporator drain so that we are making sure it's clear so it doesn't drip any water on top of the furnace or air handler or into the environment that um, the that the unit actually is sitting in for it. So just like the hat up here, a little giant hat, we can put a little giant pump on this and then pump it over to a sump pump uh, to get rid of that condensation coming off of that actual unit. Now, this next slide is just a documentation of the return air coming into it, the coil on top of the furnace itself, and the line set coming from the outdoor unit, and then the supply air. Uh, I want to highlight a couple of things so we can look at this. Uh, the return air is air that we are bringing back to the furnace or the air handler that we're going to be conditioning in some way, shape, or form. That is what the return air is. The supply air is after we have conditioned that air through the evaporator coil itself. We will take that air and then move that air into the environment that we are living in so that we can spread that cooler air without the heat in it out into the living environment so the individuals in there can be comfortable. Like I said, the indoor section for the refrigeration cycle itself is going to end up with the evaporator coil, the metering device basically slapped right onto that evaporator coil, and then a filter of some sort, a return air, a supply air, and then an air handler or an air moving device of some sort, such as a furnace or, like I spoke before, an air handler. This is just another depiction of the system as we're looking at it. This is a split type air conditioning system. We see that the condenser is sitting on the outside of the house. That is where the condenser coil, the compressor, are going to be sitting, along with the fan that's going to be moving that outdoor air over the condenser coil to get rid of the heat that we have picked up inside of the evaporator coil itself. On this one as well, we are seeing the return air, the filter, and they are using the term on this one, cold air return duct or conditioned air coming back to this so that we can take this air, condition it in some way, shape, or form, and then put it back out into the supply for the conditioning of the house itself. Now, the indoor section might be a furnace, air handler, or electric furnace. It might be there's electrical components on the inside of it. Dealing with the split system, the 24 volts will come from the indoor section, will go up to the thermostat. And then from the indoor section, a control wire will be ran out to the outdoor unit so that we can turn on and off the condensing unit as we need cooling and heating on that particular day. Our air conditioning section sits on the outside. We'll have the compressor, the condenser coil, the condenser fan as well. We'll be dealing with the electrical components on the inside of it. Code requires us to have a disconnect switch for the outdoor unit. Anytime that you're dealing with equipment that is pretty far away from the breaker, we have to have a means of shutting off the power to that unit very quickly. So we always like to say within 5 feet or within reaching distance of the condenser. That is where you're going to be placing the disconnect switch. Now, your condenser pad sits on the bottom of the condenser itself. It's right down in here. We're going to make it nice and level on that particular unit so that we can keep that unit looking good for the customer while we're servicing this unit from year to year. The condenser coil will get dirty. It will get dirty with dirt. It will get dirty with cottonwood if you are living by a river. You'll have quite a bit of cottonwood sitting around. So we'll need to clean this one periodically from time to time. And we'll do that with our coil cleaner, which is acidic, and it will eat away at the dirt. And we'll use water to wash away the dirt and the coil cleaner that's on it. We will show you later on how to clean these properly, going through the actual air conditioner and cleaning a condenser coil, replacing the fan, but as well during this session you will be changing out a compressor on a condenser as well. We're going to stick with the outdoor unit here as we are looking at the condenser. The condenser may have what we call a stacked coil. That is two coils that are pressed together. So two rows of this guy right here. We'll have them butted up against each other. And then that basically, they do that to cut down on the size of the condensing units for there to reach the efficiencies that the government has told us that we need to reach for these particular units themselves. So different types of designs are out there. We might have a single pass coil, we might have a stacked coil on our particular units. Um, and then there's different ways that we are designed to move the heat out of the coil as well. So the different designs of them are side air discharge, top air discharge, horizontal discharge. And I would have to say that for the most part, our mini split applications are going to be our side discharges. And then for most of your units out there, we are going to be dealing with a top air discharge for our particular condensing units that are going to be on our systems themselves. So let's go ahead and we're going to be discussing our different types of evaporators that we are going to see on our systems themselves. There are many different types of designs out there. Most part, there's going to be um, A coils are the most famous type of evaporator coil that we have. Most manufacturers are producing them in such a way or such a form that they are putting them on top of the furnaces or putting them inside of air handlers for that. So Rheem, Ruud, Carrier, Bryant, Trane, American Standard are all systems that are going to be dealing with various designs on their evaporator coils, trying to get different efficiencies out of them for the government to sign off for them to produce this type of stuff. So our A coil, when we're looking at it, well, kind of looks like an A. So you can see that on this coil itself, that the metering device is actually right there. And that metering device is basically slapped onto the evaporator coils in a lot of our air conditioning applications. So if you're looking for that metering device, there it is. Look for the evaporator, and then you'll see the metering device right there. And that could be a TXV, EXV, it could be a piston, could be cap tubes, but although cap tubes, you're not going to be seeing them very often anymore um, on our systems themselves. But look at the design of that particular coil, and it looks like an A. This is a slab coil. We see these a lot in our air handling units, a lot in Carrier, a lot in Bryant. Sometimes our trains have our A coils in them, but our manufacturers such as Carrier and Bryant, they're going to be dealing with a slab type coil on that particular system itself. Where the metering device is going to be setting on this particular unit is somewhere right in that area. You're going to have a drain as well on these evaporator coils. These can be set, mostly they're slant in I'm sorry, H coils and slant coils look very similar in nature. H coils can stand vertically or horizontally. This is what we refer to as a slant coil on our particular units that are out there. These are our H coils. H coils are usually found in spaces where we don't have a lot of room on our system. They don't take up a lot of space vertically. I mean, vertically they do, but not horizontally. So we can slap these guys in and accomplish the cooling that we want to. Different manufacturers have different types of designs out there for our systems. And the last one that we're going to be looking at, we're going to be coming out with a lot of aluminum coils. I haven't seen many micro channel coils in our evaporators yet, but I believe that they are coming. And by the time this video is out, you will see those micro channels in our evaporators. They just increase the surface area of that particular unit very well, so that we'll be able to lessen the amount of room that our evaporators are going to have to take up within our units themselves. So microchannel design, very small holes, a lot of surface area within this space, and these direct their way this way. The fins on all of these evaporators are going to increase the surface area of these evaporators, and they're going to offer us the heat exchange that is necessary to absorb the heat from the air passing over it. So when we are actually dealing with the evaporators themselves, there is one rule of thumb that we must follow for these evaporators. code prohibits specifically an evaporator on a gas furnace, LP furnace, or oil furnace, that the evaporator is set on the return side of that furnace. The reason for this is that condensation will build up inside the heat exchanger because cold air is going to be passing over it. It's going to have access to warm air on the other side of it through the flues that are sitting there, and it will condensate on the inside of the exchanger, causing that exchanger to rust out very quickly. And I know that a lot of rooftop units have our exchangers after our evaporator coils, but as far as our residential systems are concerned, we do not want to put the evaporator on the return side of that system because of this. Discussion of the evaporator as we continue on this air conditioning journey. The evaporator mostly has plastic drains. We used to make them out of metal. They would rust. We would have to replace them. Manufacturers are coming out with plastic drains now. The only problem with our plastic drains is if our furnace or LP gas furnace or oil furnace if it overheats, that it could melt the plastic on that evaporator drain. But it's better for us to have a plastic drain, knowing that all of the moisture that's going to be in these drains is going to be taken away and not dripped on top of anything because we rusted out that particular unit. I talked about this previous, that the aluminum fins on that system are used to increase the surface area of the evaporator so that we're able to absorb more heat off of it. And then we have air handlers or furnaces that are capable of being placed in multiple positions on our system. Now let's go through a couple of these positions so that you have a better understanding of what's going on and why we don't want to put the evaporator on the return side of these systems. Furnaces can be multi-position furnaces. This is why we have different types of evaporators out there: A coils, slant coils, slab coils, H coils, micro channel type of evaporators, is because we can place our furnaces in multiple positions. Now, furnace number 1 and furnace number 2 are basically, they have a H coil that's sitting on top of them. 1, 2, and 3 all have H coils, and you can see the different ways that we can use that coil to be placed on the furnace itself. This is a upflow furnace, number 1. Number 2 happens to be a counterflow furnace, and then number 3 happens to be a discharge right or horizontal right application for an air handler or a furnace that we're going to be placing within this individual's house. On the other side of the house, we have 4, 5, and 6. And what we're seeing there is a cabinet that for the most part is going to be housing an A coil type of evaporator in them. We can see that we can still multi-position the evaporator on the furnace to be upflow, downflow, or horizontal left or horizontal right application. It doesn't matter a lot about these systems and the positions that we can put them, because we have many ways that the manufacturer has given to us to actually position the evaporators, run the drains so that we can effectively cool that environment down inside the house. Now, the air conditioner are going to have a couple of different types of compressors on the outdoor unit. We're going to discuss those different compressors now. Most of the compressors that you are going to be running into in the air conditioning side of a system are going to be cooled by the gas, the return gas coming back to the compressor. We're talking about the refrigerant actually cooling the motor windings of the compressor, and then taking that heat over to the condenser and then jettisoning it into the outdoor air. The 2 compressors that do that are the reciprocating compressor. It's a can type of compressor shown here on the left. We'll look at it a little bit more in depth when you're in the classroom, but this compressor is cooled by the suction gas. I guess the most important thing that we can look at as far as that's concerned is we're looking at a discharge or a hot gas line that's coming off the bottom section of this compressor. On the top section of the compressor, we have the suction line. As the cool suction line comes across, it's going to go on top of the compressor, drop down to the bottom, where it's going to be pulled into reciprocating pistons and then compressed and brought into a higher pressure coming out this smaller line on the compressor itself. These are very easy to diagnose, yes, for trouble, and they are very easy also to look at and understand that they are a reciprocating type of compressor. Another compressor that we're going to be finding in smaller systems, but it's going to be becoming more popular in our air conditioning systems because of its ability to ramp up and ramp down. And we're talking about our modulating compressors. Most compressors that are modulating are going to be rotary type compressors. Rotary type compressors, if you were to feel the can on the outside of them, are hot, very, very hot. That's because we're using the discharge gas temperature to cool off the windings on the compressor. It is a very efficient compressor, one that is used in a lot of window air conditioners, and it is very easy to look at and understand what's going on with this type of compressor, and that it's a rotary compressor because of this device right here. And that ain't showing up very well. Let's go to our yellow. This device right here, and we'll do it in green so that we can understand it. And it's that device that's sitting on that rotary compressor right there. That is an accumulator. Anytime that you have a rotary compressor, any liquid refrigerant that gets into it, well, you might as well kiss it goodbye because that compressor will not pump anymore. So the protection device for that is an accumulator. It accumulates liquid refrigerant. We shouldn't have any coming back to our compressor, but if it is, we're going to go ahead and boil it off into a vapor by that device. That is how you're going to know that you have a rotary type of compressor, is if you have a accumulator that is attached to that compressor itself. Like I said before, it's cooled by the discharge gas, and the reason why they can do this is because the discharge gas is actually cooler than the motor windings. Motor windings will give its heat to the discharge gas, and then it will flow into the condenser, and we'll get rid of it in that fashion. The last compressor I want to look at, and it is the compressor that is the most, it is the best compressor that we have in the industry. They are coming out with modulating scroll compressors, so you're going to be seeing it in that industry quite a bit more. And it is the scroll compressor made by Copeland. There are knockoff brands made by about every manufacturer out there, but Copeland was the first ones to come out with the scroll type compressor on it. What do I want you to know about the scroll type compressor? That it is cooled by the suction gas, and that heat's going to be taken off of the windings, taken to the condenser along with the latent heat, the heat latent vapor that's coming back from the evaporator, and going to go to the condenser, and we're going to get rid of it in that way. The best compressor for handling liquid refrigerant is the scroll compressor. You can notice that on the side of it, there is no accumulators anywhere on this compressor. Now they do protect it in a way. Copeland will say it's not a liquid refrigerant compressor, and I would agree with them. It's a vapor only pump, but the scroll set that's on the inside of it can happen to separate out, causing the liquid to flash into a vapor, protecting the compressor from damage from the liquid refrigerant.
Well, continuing on our
on that
discussion
particular
for
system.
air conditioning, and we've looked at split units, we've looked at mini split applications, and now we're going to be getting into the packaged units. These units are factory charged. Everything that the factory wants in it is in it. If we can order it with economizers or 2 stages of compressors, but for the most part, our systems are going to have they're going to be brazed at the factory, sealed at the factory, wired at the factory. And all we're going to have to do with these units is hook them with the power supply hooked up to them, and then the 24 volts as well hooked up to them is going to them. So all the components are built into the cabinet itself. And then air is ducted to that cabinet through something that we call a roof curb, which we're going to look at in the next slide. This one just happens to have two compressors on them. I do not believe they're scroll compressors, but Trane has a couple of compressors that kind of look like scrolls on their units, and that's what we're seeing on this particular uh, packaged rooftop unit. Now, the actual unit itself that we're going to be looking at, the package unit to our upper right has all the components in it. The refrigerant's in it. It's been brazed at the factory. The compressor, the condenser fan, the evaporator, and the metering device are all there, with along with all the electrical components that go along with this particular unit. It can be gas, it can be electric, um, for different applications that we're going into. But a couple of things I want to focus in on here is the roof curb at the bottom. And that is what the rooftop unit is going to sit on when it's going to be attached to a building on the roof. On to our right, we actually see the asphalt roof here. And then what we will do is we'll come in and we'll install a roof curb onto the roof, and then we'll run our ductwork off of that roof curb down into the actual places where we need to return the air to the unit and then to supply the air to particular areas that are out there, as seen in a couple of the different pictures that we're looking at on this PowerPoint. We have a return air duct here. We have a supply air duct there. And the rest of these spots that are on this roof curb are there for merely support of that roof curb. And the only two spots that are going to be open to the downstairs or the lower environment are going to be those two spots that we're looking at. On this particular one, the roof curb, and when I'm on the left-hand picture, the return is noticed in the red, and the blue, the supply is noticed in the blue arrow right there. And these roof curbs are made specifically for the different types of units that are placed on them. So these units will drop right down onto the roof curb, and then along the roof curb, we will put what we will put a gasket along the roof curb, along the edges of it. And I know it's a horrible, horrible drawing that I'm doing for you here. We'll put gaskets right along all those metal parts on that roof curb, and we will set that unit right on it, giving us a weather tight seal. Now, the roofers will come back and they will encompass our roof curb with the asphalt or the rubber roofing that is attached to the building, so that we have a nice weather tight seal for that application. We can also ground mount our packaged units, and we can see that the air conditioning has been ducted into the house in this direction, and we'll come into the side of the rooftop unit, and we'll have a supply air and a discharge air for our units to be able to operate on the ground. We can see that, yes, packaged units do have a drain on them. And yes, we do need to trap that drain because air can get sucked up into that drain, causing the condensate water coming off the evaporator coil to back up into the unit and then to spill over into the occupants of the either building or the occupants of the occupants of the factory or wherever the rooftop unit's going to be installed. So, looking at advancements in the air conditioning industry, high efficiency condensers, two-speed compressors, modulating compressors are all things that we are really going to be seeing uh, take shape for us and also for you as we are moving into sizing equipment and running equipment in a more efficient way. Now, your two-speed condensers or your two-speed compressors have been out there for a while, but we're really starting to work into modulating compressors on our split type of residential systems. Beforehand, the only thing that really had modulating compressors were the mini split applications, but now we're starting to get into it into the split applications as well. We've oversized the coils. on the outdoor unit. And what that does is it drops the pressure on them. So we're consuming less electrical energy as the coils are oversized. Two-speed condenser fans are used just in case we are running these units in lower temperatures. We'll have one speed for the lower temperature, and then if the temperature gets up to operating conditions of an air conditioner, like 95-degree outdoor temperature with 73-degree wet bulb temperature, then we will end up running the high speed on the condenser fan because we need to get rid of more heat. Now you're going to be running into modulating condenser fans as well, and not only the two-speed. And that's what you're going to be seeing on um, a lot of our systems that are modulating, as far as Trane, Rheem, uh, Bryant, Carrier, Rude, and whoever is developing these are going to have these modulating or ECM type motors that are going to be running. It provides for us opportunities to dehumidify the house quite a bit better than what we used to um, on those systems. As far as our air conditioning, we're continuing looking at our metering devices. We've moved away from the fixed bore type of orifice and then are moving more towards the TXV and the electronic expansion device, or the LEV, or linear expansion device, like you'll see on Mitsubishi units that are out there. What these metering devices are going to provide for us are a greater ability to adjust to evaporator demand by by filling the evaporator with more liquid refrigerant or giving it less liquid refrigerant depending on the load that the evaporator is going to be on. It's going to provide for us greater efficiencies for our units themselves. As far as our refrigerants are concerned, 410A is going away because they've deemed it to be a problem with global warming. 400 series refrigerants in general are going to be the older ones are going to be moving away, and we're going to be moving into new refrigerants that are mildly flammable or have a mixture of refrigerants that in them that are flammable themselves. R22 has basically been decommissioned from a lot of different units out there. 410A is about ready to be decommissioned next year, 2025. We're going to cut back production to 2013 levels and then drop that in a percentage wise all the way down to where we're producing 10% of the actual 410A that we've been producing over the years. 407C, MO39, R22D, R422D are all refrigerants that we're using to replace R22. 454B, that's the new refrigerant that all the manufacturers have decided to go with. And what Carrier did was they came out and they went with this refrigerant, and all the manufacturers are going to have to follow up on that and start to use this refrigerant for our air conditioning mode. This is the one that they found um, to be beneficial efficiency wise, and also global warming potential is lower on it. But I can see within the next 5 years them moving away from this refrigerant as well into another refrigerant on that system.
Well, continuing on our conversations about air conditioning, we're going to be looking at the air side of the system. Now, before, when we looked at the refrigeration cycle, we were just looking at what was going on with the refrigerant that was inside the tubes or inside the condenser, the compressor, the metering device, and the evaporator. But one important aspect of refrigeration is airflow. We'll go over this more as we are actually introduced into duct sizing. But the air side components of our ductwork, we have a certain quantity of air that must pass over the evaporator in order for us to get the proper cooling for that system. In order for the correct superheat and the correct subcooling and the correct temperature difference on the evaporator to be given. Now, for a normal system, we are looking at 400 cubic feet a minute of air per ton of refrigeration. So we use the terms CFM So 400 CFMs per ton of refrigeration. And that is the airflow that we want off of that system. Now, that airflow is going to be distributed throughout the entire structure. So if we ended up with a 2-ton system, we'd end up with 800 CFMs of air flowing out of that. We'd put 150 CFMs into a couple of different rooms, depending on the heat load calculations that those particular rooms needed, until we have exhausted in totality the 800 CFMs of air needed for that system to operate properly. Now, we can use different figures depending upon moisture removal or certain arid conditions, such as in the desert. So, for moisture removal, we want to slow that fan speed down. Then we'll end up with more latent heat removal of that air. We'll get more moisture content out of it if we slow the fan speed down. And then in the desert area, we want to speed that fan up. So we're looking at 450 CFMs for our deserts per ton of refrigeration. So in different climates, you will want different aspects of airflow across that evaporator coil. So we'll end up moving the air either slower or faster, depending on the environment that we are actually in. So typically, when we're looking at airflow out of the register and air temperature coming out of that register, we're looking at a 53 to 58 degree temperature coming out of that register. Now, for aspects of understanding what type of temperature we should be getting off of an air conditioner, we'll use return air coming back to that unit, and then we'll subtract 17 to 20 degrees from that system, and that's typically what we'll be getting is about a 20-degree drop off of our evaporator for a working air conditioning system. Now, depending on the airflow of that system, I can simulate a 20-degree drop easily by restricting the airflow or increasing the airflow. I could cause it to go lower, but we need 400 CFMs of air. And at 400 CFMs of air, with an air conditioner that is charged correctly, we should be getting a 17 to 20 degree drop from what the return air temperature is to the supply air temp. And that is typically between 53 and 58 degrees on our system. Now, we talk about that because our return air is sitting somewhere between 73 degrees and 78 degrees within the house. And you're saying, well, that's way too warm. Well, for some people, yes, that's a really warm temperature. And that mainly has to do with the type of humidity that you have in the air for that system. If our humidity level is really high, then yes, 73 and 78 degrees will feel relatively warm. But if we can control that humidity in the air, then we can control the comfort of the evaporation of the skin, of the water off of the skin in that. So typically, if you're dealing with 73 to 78 degree return air temperatures coming back to the system to be conditioned, then you'll end up with a supply air temperature of 53 to 58 degrees for that. Well, hey, that concludes our talk on the air conditioning system, the different components that you will see within it, the amount of airflow for that system, the different components, and the jobs of those components within that system. I hope that you have learned a lot. We'll have a conversation later about the diagnostics of air conditioning systems, and we'll have a talk later about the different types of distribution systems for the airflow of the AC system. This concludes the PowerPoint presentation.